Welcome to the deep dive. Today we're jumping into the online encyclopedia of integer sequences again. We're looking at A000364. You might know these as the Euler numbers or maybe secant numbers or even zig numbers. Our goal really is to get a feel for what these numbers are actually counting and how they link up to the functions that generate them.
Right. It's a really interesting sequence. It sits right at that intersection, between combinatorics counting things and analysis functions and calculus. The defining feature, the starting point, is usually its exponential generating function. The EGF A000364 gives the coefficients when you expand secant of x, which is just 1 over cosine of x. But crucially, it's only the coefficients of the even powers of x in that series. So x0 by 2 by 4 and so on, divided by the factorials.
Okay, so we're taking second series expansion, but only picking out the even terms. And that gives us, let's see, the first few. 1, 1, 5, 61, 1385. You mentioned counting. These numbers apparently solve something called Andre's problem from, the 19th century? And the name zig. I assume that relates to the counting part. What exactly is an alternating permutation?
Yes, exactly, Andre's problem. An alternating permutation of, say, the numbers 1 up to n is just an arrangement where the numbers go up, then down, then up, then down, or the other way around, like a zigzag. Now, for this specific sequence, A000364, we're dealing with sets of even size, like 1, 2, 3, 4, or 1 to 6. And A2 on, the term corresponding to 2-pen elements, counts the permutations that start by going down. So C dar C22, then C22, then C23, then C42, and so on. Down, up, down, up.
Down, up. Okay, let's try to make that concrete. The sequence goes 1, 1, 5. So that 5 corresponds to N4, right? Or rather, 2N4.
Yeah.
$2D is 5, 5. So you're saying there are 5 ways to arrange the numbers 1, 2, 3, 4, so that they start high, go low, then high, then low, like maybe 3, 1, 4, 2. Is that one 31, 14, 42? Yeah. Or the example you gave earlier, 4, 2, 3, 1, 4, 2, 23, 31. That works too.
Exactly right. There are precisely 5 such arrangements for the set 1, 2, 3, 4. That's what the number 5 means here, combinatorially.
Okay, that clarifies the counting. But it brings up the other question. Why on earth does secant know how to count these? That seems unexpected.
It is pretty amazing. That's Désiré André's big theorem. He showed that the generating function for all the alternating permutations, both up, down, and down, up, is actually secant x plus tangent x. 1x equals sec x plus tan xu. It's beautiful, really, because secant is an even function. Its power series only has even powers of x, and tangent is an odd function with only odd powers. So the second part naturally generates the coefficients for the even-sized permutations starting down, are A000364, and the tangent part generates coefficients for the odd-sized permutations starting up. That's sequence A000182, the tangent numbers.
So the generating function itself splits the problem perfectly based on the function's symmetry.
Clever.
Yeah. Now, these numbers, 1, 5, 61, 1385, they get big really fast. How did people calculate them back in the 1800s? Surely not by listing permutations or Taylor expanding secant by hand.
No, thankfully not. There's a much simpler way, purely arithmetic. Seidel published an algorithm in 1877. It's sometimes called the Boostrifidon Transform, which is a great name. It basically involves creating a triangle of numbers. You build it up row by row, using just addition, kind of like Pascal's triangle, but with a different rule, zigzagging back and forth. It generates these secant and tangent numbers very efficiently. No calculus needed.
Interesting. So a purely combinatorial way to calculate them, too. Now, you called them Euler numbers earlier, but I usually think of Euler numbers in Euler's Euler as being related to hyperbolic secant, secantet, and they have alternating signs. How do these relate? And hang on, I read somewhere that all the numbers in A000364 are odd. 1, 1, 5, 61, 1385. Yeah, they are. Is that always true? That seems weird for a count.
Good questions. Yes, the standard Euler numbers, often defined via hyperbolic secant 1 cos t, do alternate in sign. Our secant numbers, A000364, are essentially the absolute values of the even-indexed standard Euler numbers. So A is eta tar, or more formally, eta eta. They're very closely related, just differing by a sign sometimes. And yes, astonishingly, every single term in A000364 is odd. It's a known property. It falls out of the combinatorial structure related to symmetries. It's not obvious at first glance, but it's true.
Wow. Always odd. Okay, so wrapping this up, as we step back from the counting in the series, what's the sort of final takeaway? What's the bigger connection here?
I think the most profound connection takes us back to analysis. Remember the generating function. Where does that function break? Where does it go to infinity? It happens when cos equals $1. The first place that happens, the closest pole to 0, is at 6 equals pi to 2. And that value, pi 2 by 2 determines the radius of convergence for the power series of sets.
Yeah.
So the growth rate of these numbers, these counts of down-up permutations, is fundamentally limited by pi at 2. It's a beautiful, if unexpected, link-counting discrete arrangements tied directly to a fundamental constant of geometry and analysis, pi.
Pi limiting how fast we can count zigzags. That's
Yeah.
definitely something to think about. A great place to leave it. Thanks for the insights.
My pleasure. It's a fascinating sequence.